So hello everyone. Hello. Welcome to our today's seminar. It's a great pleasure to introduce you, Professor Siyuan Xing. For some of us, the Simon. He's a poly in San Luis Obispo, and his primary research interests have been on nonlinear dynamical systems, application analysis, so on. But in the last 3 years or so, maybe, or 4 years.
3 years. Yeah.
3 years, yeah. He has been branching out and working on very interesting problems revolving around neural networks, model discovery. And today he's going to talk about the CombOpNet scaling SINDy for high-dimensional dynamical systems.
Thank you, Stasis. It's such an honor being here. I really like the environment here in the San Diego State. So the campus here is very beautiful. So today I will be talking about a CombOpNet or Combinatorial Operation Neural Network. This is used for scaling SINDy or Sparse identification for nonlinear dynamics for high-dimensional dynamical systems. So to start, I want to kind of give a background and talking about the challenges and also kind of our motivation for developing CombOpNet. So in nature and also like physics, there are a lot of the complex spatial temporal phenomena like pattern formation, turbulence, and synchronization. Traditionally, the way we approach these problems will be derive equations from first principle or empirical laws. And nowadays, many of the systems actually have abundant data, but we actually do not have the knowledge about the governing equations. And these systems, often involve hundreds and thousands of variables. So we have seen a lot of the order reduction methods being applied, to kind of study their dynamics. And our traditional methods here are somehow limited to low-dimensional dynamical systems or systems with scarce data. And we also seen that neural networks actually being used extensively, for prediction, and also identifying, characterizing the dynamics. But neural networks here, they are, naturally just kind of black box, non-interpretable. So it's actually hard to extract physical insights that are actually crucial for physics and engineering applications. So there is actually a need for, actually an urgent need for data-driven discovery of governing equations, for scientific understanding. The current gap here I want to talk about is if we look at those neural networks, the reason we use them is because they are universal approximators. And if you compare, the early single layer neural network and the more recent deep neural networks, and the difference there is for deep neural networks, the structure itself, the computational structure itself, allows us actually to scale it to very complex problems, with extensive data. But we have been actually, I think in our community for scientific computing, there are a lot of attention actually focused on the universal approximator. But the structural advantage for this neural network for accelerating computing is somehow, unexplored. And the key question here, if we wanted to, what we can ask here is, if there's a way that we can actually design new neural networks that are interpretable, and then we can also kind of embed some of our traditional methods. This way we could take advantages of our computational efficiency of neural networks, their structural computational efficiency. At the same time, we'll also be able to preserve the interpretability. So the network itself will give us interpretable, predictions, and the network itself, you look at the ways, is understandable, what actually it is doing for each neuron, each way. So that kind of brings up our approach here. So develop this interpretable neural network. Later I'll talk about this is called a CombOpNet or Combinatorial Operation Neural Network. So doing so, we can kind of gain a interpretability, and also we can also have the efficiency, for computational efficiency for high-dimensional systems. All right, so this is our motivation, and in my following presentation, I'll just kind of break my presentation into several sections. I'll start with matrix formulation of SINDy, sparse adaptation of nonlinear dynamics. So there are actually a lot of methods here for discovering dynamics, but I will be solely actually focused on SINDy today, and this is our main thing. So there, there are also like a symbolic regression, okay, but this is going to be our main player today, and I will be talking about the curves of dimensionality, introduced by SINDy if you want to scale it to high dimensional problems and also like problems with higher order nonlinearity. And I will talk about, I'll introduce the CombOpNet. I will do some comparison about the memory consumption of CombOpNet, and you will see that this network is able to actually reduce the SINDy's computational load, okay, cost by orders of magnitude, okay, from like a gigabytes level probably to kilobytes level. So that kind of differs. All right. I will show some results, okay, for CombOpNet with and without noise, and I will show this network itself can also be used to do extrapolation, which is one task that like traditional neural network like usually kind of have challenges. Okay, I also talk about the scalability of this method with big data. Right. About the SINDy, okay, we usually will consider a dynamical system in this form. You could also add the control on U here. And the main assumption here is in our dynamical systems mathematic form, we're going to assume the vector field here, the vector field on the right hand side is actually only contains a few linear and nonlinear terms. And SINDy seeks for approximating this vector field using a library of candidate function. So we're going to define this theta. So you're going to see like my symbol here is kind of slightly different because here I use mass type, and there's one that's embedded equation like formatting in Word. So like in PowerPoint. So sorry about that. Just kind of put out me with that. All right. All right, so we want to use this kind of like collection of this candidate functions, and then we do just kind of do linear combination of them. So we'll use the right hand side here to approximate our fx. All right, so the C here will represent the coefficients of those candidate functions. And one example here is, if we look at our classical Doppler oscillator, this is a classical way we represent this dynamical system. But if we assume this is our candidate functions, we have this kind of linear term, this quadratic terms, okay, and this is the cubic term, and we can also represent our fx, our vector field, by C and also theta here. So just matrix multiplication, and you will see this is a sparse matrix, okay, a lot of zero there. And this kind of align with our assumption here. Most of this kind of like the vector field will only contain like a few terms here. Okay. Right. So suppose we have a set of measurement here. The collection of this measurement of our state and also the time derivatives. The time derivatives could also be computed using finite difference. So it will be fine. We would just kind of have a collection of our states. And we can define the time derivative data here, okay, just kind of like this kind of sequence, and this is going to be the matrix for our candidate functions. So the x to the power of d here actually represents the matrix composing the color vectors, and then give you all possible time series generated by these degree polynomial x. So in this way, you can actually assume your candidate function to be constant and linear term, okay, quadratic term, and you can also have sine and cosine nonlinearity here. Okay. Right, and then we can actually write our dynamical system in this form. The syntax here, the notation here is a little bit different. I do a lot of programming, so sometimes I would say like syntax, okay, but I should do that here. All right, so because they actually all for data, so you can see the notation is slightly different, but still, we are using this kind of like a collection of this. Now this is data matrix here, is our like a candidate function, okay, and then this will be also just be some numerical numbers. It will be a big data matrix, and this C here, capital C, is our coefficient we wanted to solve, and based on our assumption, this C is going to be sparse. Okay, we only have a few non-zero terms here. Okay. And then we can actually formulate the problem here as to like sparse regression problem. So we want to, have our candidate function, okay, multiplying the coefficient matrix here, and then use this one to approximate our vector field. So our goal here is to find this coefficient matrix which can minimize this error. Okay, at the same time here, we actually impose this R as this kind of like a sparsity promoting operator. So people do L1, okay, norm L2, like lasso range, probably you have like know about it. And also like you can also do SDM as okay. But the point here is this R will help us during the training process, during the optimization process. This R will help us, to promote the sparsity of the matrix Cassi, okay, our coefficient matrix. And our goal here is to find this kind of sparse Cassi matrix here, giving us the best approximation of the vector field. All right. So that's about the formulation, the matrix formulation of SINDy. And well, the problem here with SINDy is if you wanted to scale it to a high dimensional problem, you're going to face this force of the dimensionality. If I have a that's fine. That's fine. Okay. So just think about if you are thinking about those kind of counting the number of those combinations of polynomials. So for example, we could have x and y. This is our linear term, and if we count the number of the quadratic terms, we're going to get x squared, okay, xy, and y squared, okay, right? And if we are if we are counting number of the cubic terms, we go to x cubic, okay, x squared, y, and xy squared, and the y cubic, all right? Okay, so if you kind of scale, increase your order of nonlinearity, this number is going to increase exponentially. Worst case here, if you also wanted to increase the number of those states, okay, and then the number of the combinations of those polynomials, is going to just increase also exponentially. So it will follow this kind of formula, this kind of like a factorial, this formula. The n here represents the number of variables, and p represents the number of the highest order of nonlinearity. Okay, so this is kind of like crazy. If you look at this case where we have the p actually fixed to 3, and we increase the data dimensions, and the scale here is 10 to the power of 7. So when we get to 100 dimensions, the number of those possible combinations of those polynomials up to, well, when I say the combination, I include a linear term, like cubic term, quadratic term, cubic term, and all the way to piece order polynomial. So this number is just going to increase exponentially, right? And then how can we solve this problem? And obviously, if you apply SINDy, for this problem, your computer is just going to die. Right, it's just going to take 1 million years, to get your result. Okay, so how can we solve this problem? There are actually a lot of work on the side, but today I'm going to jump part of it. Just sort of apologize for that, and because I wanted to focus on have time to kind of focus on our approach here, and also Stasis asked me to later kind of show some of the code for students, so it probably will be easier for understand. So I want to kind of allocate some time so I can actually give you guys a demo for my code. Okay. All right. So there's one observation we can take for those nonlinear terms. So most of those nonlinear terms actually, they will just be like a combination of those. Like the kind of polynomial here, okay? So I think the distinct feature here, you look at this term, this is actually separable. So x1, x2 squared, x3, you can think this is a multiplication of x1, x2, x2, and x3, right? So what is nice is you can actually relate the right-hand side here with the forward propagation in your neural network. So I can actually allocate this neuron to x1. So this is a different example. So the second one, I said this is x2. Okay, so if you do forward propagation along this path, okay, it basically will give you that nonlinear term. Does that make sense? Okay.
So the number of layers determines the highest order.
Exactly. Right. So if we just kind of add those kind of shading neurons here, and then make it a feed-forward neural network, and basically this feed-forward propagation will give us all the possible combination of those kind of like the polynomials up to P order, where P is actually the depth of our network. Okay, does it make sense? Right. Yeah. So this brings up our like neural networks here. So we also have an input layer, hidden layer, and output layer. And this input layer, different from multi-layer perceptron, we actually share the input data, with all layers. Okay. So the theta one here is kind of like a candidate function, or just kind of like a neuron. Okay, for each layer, it could take a constant. It could just take this monomial. It could also be sine, cosine. But the point here is the forward propagation will automatically actually help us to get all the possible combinations of those polynomials. Okay, so we have no bias in this network. Okay, we also have no nonlinear activation function, no sigmoid. It's basically just kind of doing multiplication. It's just kind of like a combinatorial operation. So we call it a combinatorial operation neural network or CombOpNet. Okay. Right, so this is actually the expression for the output of this network. We start with the first layer. Okay, this is the first layer, which is basically give our input data, okay, to all those kind of candidate functions, just monomial, constant, or sine, cosine functions, and then we multiply matrix multiplication, okay, and then we get an input to the second layer, and then we do this element-wise product. Okay, so and we get an output of the second layer, and then this is going to be the output of my second layer, and then I do matrix product. Okay. Matrix product with the next with the W2 here. Okay, all right. So one thing I want to kind of mention here is our goal here is not to actually get a universal approximator. Instead, we're trying to use this feed-forward network to accelerate our computation, because it's so easy actually for us to kind of get all these possible combinations. If you do it a hard way, think about the previous factorial formula, it's going to take you forever. Okay, but this one, okay, you just kind of stack those layers. All right.
We say that you share the input layer with each layer. Could you expound on that a little bit more?
So basically, those kind of like theta 1, theta 2, theta k, this is our our neurons for each layer, right? And basically, their input will just be this. Let me put this way, okay? Let's say they just use a monomial, so have 1 x, or we follow the notation there. x1, x2, and this is xk, right? And the second layer, you're going to do the same. Okay, so each layer is just kind of augmented, by 1 here. So this is going to be your input, and you kind of just feed it to each layer.
So the fundamental operation of the multiplication.
Just multiplication, yeah, multiplication and summation.
Yeah, where you have this matrix multiplication in the previous operation.
Right.
Is sine and cosine sufficient to handle any neurons, nonlinear neurons?
Well, we just put a sine and cosine. Definitely, you could also add a exponential function, log function here if you want. That's right. But this is kind of like just an example for like our functions with neuron.
What about complex candidate functions?
Could also do that. Yeah, at Riesman's level, TensorFlow is very easy to add.
The weights W, they are either 0 or 1, or you actually
They are actually just the real numbers here.
Because at the end of the day, you multiply things, so
yeah, we will do pruning.
One.
So at the end of the day, the weights less than some threshold, we're going to put it. So what here happens here if you have this kind of like nonlinear term x2, xy, and say if this is kind of like original SINDy formulation, this is your weight. Just gotta give index I. Sorry, my math is not good. Okay, so in the forward propagation, we basically break up this one, to let's say omega k times maybe omega j. Okay. So it's kind of like the decomposition. It's a network decomposition of this matrix formulation.
So is the sparsity imposed by the weight matrix?
Later, yeah, we would do that. Sparsity will be imposed by the weight matrix. We're going to do like network pruning, and many of those kind of weights will just be zero in the end of the day. Yeah. Okay. Good. Should I continue? All right. All right. So we have two different setups here. One is a parallel structure. You can just kind of like stack, many different layers of many different CombOpNets here. Each of them will be allocated to one dimension. Okay, so we can actually use this network to approximate n-dimensional problem. And then this is the loss function. Okay, and second one here is our serial structure. You could just use one CombOpNet, and you train dimensions sequentially, and each time you just kind of flash the weights and then start a second layer or the next layer. Okay. All right, and then you can just later do like a weight construction. The some folder here, you could actually use it to recover, the original ODE. So there is one step, after the training, we can do weight construction. So you can actually back calculate the original ordinary differential equations, explicit form. Okay, all right. Well, this is some common, comparison between of the memory consumption, between SINDy and two different versions. V1 is for parallel structure, and V2 is for our serial structure. And the three different figures here, we have the polynomial order from 2, 3, and 5, and the dimensions here we have 10, 100, and 1000. So you can see this is log scale. What happens here, with the cubic nonlinearity? This one, if we consider the second version here, this is a several orders magnitude reduction in terms of memory consumption. So for example, here you have probably you over 1,000 gigabytes. So we assume fixed 2,000, 3,000 the data points, and then we calculated the memory consumption of that data matrix for SINDy. Okay, so this one actually you probably will just have a megabytes level memory consumption. This is a huge reduction here in terms of the memory consumption, and this is the main reason that we can actually later I'll show you we can scale to problems over 100 dimensions.
I'm having a lot of trouble getting some sort of intuitive grasp of what's going on here.
Yeah.
Is this reduction due to the enforced sparsity system?
No, we haven't actually considered any sparsity here. In this case, so what I consider the memory I'm actually computing here for CombOpNet basically would just be the memory consumption for all neurons and also for all weights. Yeah. Okay, and for SINDy, if I can go back to early, I'm actually calculating the memory consumption for this matrix. So what happens with this matrix here? This x2 here is not just the x1 square, x2 square is actually include all the quadratic terms. So you have x1, x2, x2, x3, those things. And you have 100 dimensions. This itself, it's going to be huge. If you have a cubic term, it's also going to be a large number. So the main problem here with SINDy here is this data matrix. You needed to include all these kind of candidate functions and all different combinations, for your polynomial. And even if you have just 2,000 data points, this guy's going to blow up. So our memory we can calculate here is basically memory consumption of this data matrix.
What's the trade-off on computational power?
Trade-off on computational power.
Literal energy consumption, like flops. You may not.
I haven't actually considered. So on here, but it's I only consider the memory we need for the network. But I would say if you consider flop where you do forward backward propagation, right? Yeah. It's the number of weights is kind of your bottleneck there. So it will be like similar to that. I mean, that is kind of determined like factor. Right. Well, there is the like the pooling side, but I'm not going to go through this one very like thoroughly today because I need to kind of save a little bit of time for a later presentation. But I think the key here is because we do we write on our coding in TensorFlow, and in TensorFlow there are certain ways you need to actually work with it to do pooling. You cannot just say, okay, I'm going to set this number to 0. So there is a technique called masking, which is used frequently by machine learning community. So you do pooling like a big network. So what you do here is you're going to have like a mask matrices which have the same shape of your weight matrices. So for masking mask matrices, you have either 0 or 1. So when you do forward propagation, you multiply your weight matrix by the mask, so you can kind of zero the weights there set a threshold. And at the same time, you want to stop those kind of weights actually participating in back propagation. So your gradients should also multiply that mask as well. Okay. So, but this is just some like a technical detail here. I'm just going to quickly go through. Let me show you some of the results here, and actually, we have been working on. So we have been working on like 5 different spatial temporal systems. And this is the corresponding dimensions from Lorentz 96 Kuromoto oscillator. So it covers the quadratic nonlinearity, sine, cosine, sine, okay, and cubic nonlinearity, also with DNS and L, this kind of cubic nonlinearity here. This is our like the model here, for the Kuromoto, the lateral size here is actually, if you consider sine to cosine, it's kind of compared to like 120 degree Lorentz 96. Okay, so and this figure shows the loss. Okay, the converged loss here. So we do early stopping. The loss less than 10 to the negative 10, and we just kind of avoid the training. So most of the time, the loss here can go actually below 10 to the negative 10, and also the coefficient error is less than 10 to the negative 5. So for each cases we actually test it, like almost guarantee you actually find that like exact governing equations, with a coefficient error of 10 to the negative 5. Okay, you can recover all the terms. Yeah.
I mean, but isn't this kind of biased? Because I feel like you could just cookie cutter the neurons that you choose to put in your network for each benchmark, or did you like have it be the same or something?
It'd be the same. So like we didn't have do some artificially disable some neurons. That initially they were actually all trainable except for the last layer, which is all unified. Yeah. So just kind of same method applied to 5 different systems, and we didn't actually have any constraint.
The DNLS, is that on one dimension?
Yeah, just one dimension. That is, it's kind of complex number. We kind of treat the real part and the imaginary part independently.
Are there sufficient nodes for anything that's, interesting?
Nodes for
The nodes, 100 nodes, 60 nodes, 50
Oh,
nodes?
no. Here,
Okay,
initially we just want to show that, okay, we can go beyond 100 dimensions.
okay.
Yeah. But, this one can go higher,
Did you have any timing or was that in the next slide or something?
No, I didn't put it here. So, but this one, like less than 1 hour, you can finish all the computation, because, this one we do a training sequentially. So each layer, each dimension is is probably like I think, yeah, my math is not good. It's kind of a few seconds, I would say 10 seconds or 15 seconds, something like that.
I approve of the results.
So are these indices indexing a multi-dimension system? Are they time indices? I don't understand where you have the time on this.
Those are the indices of those state variables.
Okay.
Has nothing to relate
So
to time.
there's no range on them, so it's awful hard to tell what.
Yeah, this one we have like 100, so 100 nodes, and like this Kuromoto oscillator we have 60, and the 5-4 here is 50, and this is 50, and this is 64.
Okay, so that's the dimensionality.
It's our nodes for the like dimension, because for DNLS and AO, we kind of split it to real and imaginary parts, and then we kind of like double the dimensions here.
So those are essentially integers that specify the lattice node. Essentially, that's a couple system.
Right, so what do you do at the boundaries of this lattice? When you have I plus one and you're at you're on your last variable, do you go
For
around?
one system, we use periodic boundary conditions, and 5.4 here. Periodic one is I need to kind of check so one is the like free. Okay, so DNLs and A, I think they are free boundary conditions. So it could work with the free boundary condition, periodic boundary condition. I don't think the boundary condition itself could be a problem. Okay, shall I continue? Another thing to highlight here is data size reviews. Most of the SINDy, recommenders you see people actually do. They kind of like talking about scarce data, so it's probably like a few hundred points and a few thousand points. But here we use like much more data, just kind of show that this algorithm here can handle big data situation. Okay, all right. The reason for that is because we use mini batch training, so the data size really doesn't matter too much.
What means the numbers in the network structure color?
Oh, so this one is like 2 layers. Like this is the number of the neurons in each layer. So, okay, so because we have a constant 1, so you need to add 100 by 1. So this will be like each layer has 101 neurons. So it's actually very small network compared to
So your dictionary, how many elements are in the dictionary? At the beginning.
How many elements?
Yeah.
100. The input.
Oh, that's the nodes.
Yeah.
Why are the 3, like for the last 3 rows, why are there like 3, why is it 1 on 1?
Oh, so this one, they have like a cubic terms. So we really use 3 layers. Like number of layers kind of like equivalent to the like highest order linearity here. But we have tried, like in this one we go like 3 layers. It also works.
Oh, so that's like a list of how many neurons.
Yeah.
Oh.
Yeah. So sorry, I didn't talk about that. I'm sorry. I'm sorry. All right. Yeah. I probably need to go like a little bit fast. I think. So here is a part of our results, like 5 different systems here, and we actually just kind of showing the time evolution of vector field. Ground truths generated by numerical simulation, and this is also generated by numerical simulation using the identified system. So the accuracy here in terms of vector field, this is kind of accuracy we can actually get. This kind of in line with the accurate the error of those coefficients. All right, this is about extrapolating coherent structures. We just kind of for DNS AO, and we like pick some coherent structures, and we validate if the identified system can actually recover those identified coherent structures. So one thing I want to point out here, those are untrained data. So we use untrained initial condition and put it there, and then compare that with the full simulation. So this is another advantage of CombOpNet, because it's interpretable and it can recover the original differential equation. So if you expected that it can actually do extrapolation, but with nonlinear perception, if you change your initial training data, if you use untrained data, it is likely it will give you some something that you don't know about. Sorry. All right. In terms of the performance with noise, here we use a 5-4 system, and we calculated those MSE of those coefficients. The red line here is the median, and we can see this is kind of like a stable across different dimensions. But we do see some outer lines here when we get 100 dimensions. This usually happens only like in 1 or 2 dimensions. I think if we fine tune the hyperparameters, it's kind of only avoid. Okay, but the point here is this kind of like the error, of those kind of coefficients doesn't actually kind of like scale. Okay, it doesn't actually change. As we increase, doesn't change too much as we increase dimensions. And so we pick this 220, like actually. I would say this is actually just 10. 0.54, but it's, you convert to state space for you, this is 20 dimensions. And we can see if we add the magnitude of our noise level, this kind of like MSE of the coefficient is also kind of increase. And I think, we kind of conclusion here is the method here can tolerate a problem at, probably up to 10% of the noise. Actually still give us, acceptable, prediction here. And obviously this is the area here is, the magnitude is, the C here we use this is 2. So relatively areas are still, small. And the bottom one here, we show the, compare the evolution, okay, clean data, there's noisy data, and also the evolution of our identified system. So, because this is a nonlinear system, even if you have a very good match of coefficients, the trajectory eventually is going to diverge, right? We compare the simulation of the real system and identified system. Identified system, there are coefficients we have some error, and that kind of error, because chaos eventually will lead to divergence of the two trajectories. But it's still, for like a 10% of noise, the like the identified system, the trajectory still kind of match somewhat closely with the with the real one choose. All right, next slide here. I will show actually some scalability with big data. So the algorithm I'm comparing here is MANDY. MANDY is like a tensor decomposition version of SINDy. So you use a tensor train representation, which can actually help it scale up to like very high dimensions. So actually I forgot to put the system here. So system is still like a 20 dimensions. Okay, it's like an example from the MANDY library. But the point here is, the CombOpNet here, when you have sufficient data. So here, sufficient data here means like over like 4,000 data points. The convergence time here is somehow relatively constant. This is just kind of because we have sufficient data and use a mini batch and just it just kind of like a convergence like like rather than the same time. But the X here, and when the data is insufficient, the algorithm may converge to like round sort like equations just because we use univariate itself. This kind of approach, we need more data. Okay, but like many here, they have this kind of like cubic or quadratic complexity with data points. Okay, so what I wanted to kind of like illustrate here is, if you work on like a big data applications, the scalability with data itself, the size is very important, and the CombOpNet here you can maintain somehow constant computational speed. Although this is just kind of like a test case, but we wanted to kind of draw a comparison between CombOpNet and MANDY here. Okay, so. Let me continue. Okay, this is a conclusion here. Okay, I'm gonna kind of skip those two, and then I can directly jump to my my demo. And I'm extending the work here. I think we're actually considering the partial differential equations, and this is what we're working on currently. Well, SINDy, this has some close connections with extended DMD for Combinatorial operator, and this is another direction I think we can actually consider for future. I think that's all for my presentation today. Thank you very much. I'll be able to answer that.
How do we initialize the weight?
Well, it's a good question. The weights actually, initially we just use a random, but just kind of follow a Gaussian distribution with a zero mean and probably like 10 to the negative 3 or 10 to the negative 4, that kind of like standard deviation. The reason for that is, that actually brings up another like advantage of CombOpNet. The reason for that is, also, one is because the sparsity assumption, because the network itself eventually is going to be sparse. So, it makes sense to, make most of the weights very small starting from the very beginning. And another thing is, if you do forward-propagation here, if you have some data with a large magnitude here, because we do not immediately calculate those higher order nonlinearities, we actually use forward-propagation. So those kind of small weights can help us, avoid some numerical problems with calculating those kind of higher order polynomials directly. Yeah. Okay.
do the weights, are they? Is there a strategy to calculate weights that's based on the actual time series data? Whereas if you have certain types of time series and it looks like it approximates some sort of distribution or whatever, and then, you know, you can say, well, use strategy 47 or something like that.
Yeah, I think that's a good like direction, you know, to explore. You know, in our initial attempt, we just wanted to make it general, universal, so we can apply it to like different situations.
What computers do you have to? You have to. Oh, this one.
Yeah, so all computation is actually has been done actually on this like laptop, but it actually is very powerful. I definitely highly recommend M3 chip by Apple. You know, it's kind of faster than my desktop.
What about the M4?
Oh,
When are you
M4 is
gonna get
even
an
better.
M4?
It's even better. Well.
So this technique is kind of dictionary learning type technique, right? Did you compare with other type of dictionary learning techniques?
Dictionary.
This other type of technique.
Well, in terms of dictionary, like, you know, we can select any dictionary we want.
Yeah. Did you compare with other existing techniques?
Existing thing, we just compare with actually SINDy because that's kind of initially was going to be like sorry, SINDy. But you know, as far as I know, you know, the data master here, you can compute, you know, identify the governing equations here is, you know, sparse regression. Oh, not sparse regression, the symbolic regression. But it just cannot handle the problem, you know, we actually are tackling here. Yeah.
You apply this to problems where you know a priori that you're gonna have bounded variables are gonna be in some bounded domain.
Yeah, it's definitely in some bounded domain. I think the point here is the data itself has to be representative. So, you know, for example, there was kind of like I think one example, like a link to like Stephen Stephen's like earlier paper in 2016, sorry, 2016. So the like if you use actually a limit cycle, you know, like two-dimensional limit cycle, and then use that to kind of correct the problem, and actually it will actually give you like round results. And the reason for that is the motion itself, the trajectory converges to a low dimensional manifold, which cannot actually represent the high dimensional dynamics.
Mhm.
So I think in terms of bounded or not bounded, I think the most important thing here is like make sure the data itself is representative. And for unbounded, you know, if, for example, we have a large X, those things, it may cause some, you know, computational issues for those numerics algorithms.
Yeah, I mean, I'm just concerned, is there any situations where this, what you get out of this can blow up for some combination?
Well, okay, yeah. In that case, I haven't tried that, but one thing we could do is we could just kind of like truncate several, you know, some like finite regimes there, and I'm not sure if that will actually still be able to discover the equation, but that's kind of worth exploring.
In the introduction, you mentioned an application that you don't know the underlying model.
What?
Right? You don't know the underlying model. You have a dynamical system.
Yeah.
You have the measurements, but you don't know what the model is.
Yeah, I don't know what the model is.
Yeah.
Right.
So how do you choose the set of neurons?
Set of nodes. Oh, that's always going to be a problem for SINDy related method. Selection of candidate function is an art. That's right. Yeah, that's right. I think that's the kind of main limitation for those methods.
So how sensitive is this approach to the threshold you put on which to prove certain nodes? Like if you change the threshold slightly, is it going to give you a whole bunch of noise terms versus just?
That's a very good question. So initially we use a constant threshold, and later we kind of like make that, you know, variant with the epochs. So just kind of like yeah. So that way you can add some, you know, stochasticity to your algorithm, and you know, if you do this kind of, you know, epoch varying pruning, you know, what we'll observe is eventually it's going to converge.
But I mean, is the model gonna be as interpretable? Like, if you, depending on what threshold you said, it's gonna be either really just
Right.
on like a whole mess, or is it gonna be something very?
It's going to be if you use some unrealistic, super big, threshold. Of course, you're going to get all zero because like that threshold could exceed your dominant term, right? So in that case, you just get a bunch of zero. That's right.
The feudal library of candidate functions, is that library the deity of candidate functions, or are there like 10,000 other libraries?
1,000 other like.
Well, I'm being facetious with the word 10,000, but I mean, is there 50 libraries that everybody and their mother uses?
Most situation now, I think it would just be polynomial and sine cosine. Yeah.
So you get the polynomial from the structure, right?
Yeah.
The order. And then sine and cosines are sort of the, I don't say basis functions.
Basis
It's not-
functions.
It's not linear.
Not linear, yeah. It's not linear. But I mean, like,
Is that sort of arbitrary, or are there other,
uh,
I mean, I guess with complex exponentials, you could get all sorts of.
Yeah.
Some people need the similar type of thing, but with weblet functions. Weblet functions in there. I mean,
Yeah.
Yes, weblet neural network. That way.
Well, I just have one question about the sparsity promoting operator. I mean, Simon, can you comment about how different choices of that may affect the whole converters? Minimizer. You mentioned briefly like lasso and so on.
So our experience is L1 that is the most popular one, and but if you scale to high dimensional problem, L1 wouldn't be sufficient. You're gonna get a lot of redundant terms, because we have done comparison between this master and SINDy, and SINDy is just 100 dimensions. SINDy is able to calculate it for like a Lorentz 96. It's doable. Take a long time, but like 50% of dimensions around. But it's not actually be able to handle like a cubic, like quadratic nonlinearities, 100 dimension. Okay, can return to our topic here. So A1, okay, for high dimensional problem, okay, not work well wrong, the same as L2 and STLMSQ, STLSQ. So it's kind of like a sequential thresholding method. I think the main issue here is the selection of the threshold for that method. If you have like for small dimension, that's most time I think it's fine, but for high dimension, that number is specific, is very challenging actually to find the right number for that threshold. This is why actually what we're doing here is we have that's kind of like a apple varying threshold. You can go up and down, up and down. At least at some point, it's going to get a good result. I mean, like this is kind of based on our experience, like like what our understanding is that when you do that kind of like this kind of way to do thresholding, you gradually constrain your optimization problem to a subspace, which is more close, to like the real solution. But there is still chance that you could make a mistake, like accidentally eliminate the dominant terms. So you're going to kind of ramp it down. Okay. So you actually bring this kind of like a chance, this opportunity for the algorithm itself to kind of like go from the constrained domain to expanded subdomain. Does that make sense?
Annealing,
What?
kind of like annealing in a sense.
Yeah, kind of like that. But I'm sure definitely there should be like better like putting methods, but this is like the way actually we get it working.
I have a question. Sometimes when we try to, let's say, model some dynamical system like you're trying, right? One of our interests is maybe to know the Jacobian of the system, so we can do some sort of maybe control or design, right? I was wondering if there is a straightforward way of getting the Jacobian once you have the coefficients of your one, you know the value of the neurons, or I mean of the coefficients, or not really.
you might be able to directly do that using auto differentiation. Yeah. Because your output here is f. You do partial derivative with x1, x2, you can automatically get that from automatic differentiation, but it will just be the numerical numbers. But another way you can do it, you can use reconstructed dynamics. Give you actually the explicit form for your ODEs, and you can actually work on Jacobi on top of that.
I was wondering if you've made this available or is it published or?
The code we're going to publish it soon. So if you are interested, you can talk with Professor Stasis. There are actually a lot of problems that you can follow on for this. And what I can show you here, let me actually have my code open here. Sorry, I will be switching my screen soon.
I think for the Jacobian, if you have the equation, you can actually do this for differences and you can subtract the medical.
Yes. Yeah.
I mean, with the expense of, I don't know, double for loops or something, I don't know. So you can estimate, yeah.
And do you have an estimate for like runtime of the neural network compared to the actual dynamical system?
Actual dynamic, that's a very good question. Yeah, that's a very good question. We haven't tried that, but there is one possibility. If you actually discretize the system, you can actually get that kind of iterative, like discrete dynamic system. So that way, I don't know, because it depends on whether you compute this one on CPU or GPU. Okay, it is possible that I think for high dimensional system, that kind of like computation could be faster because nowadays the matrix computation is so optimized with GPU, but without if you do that computation using original dynamical system with CPU, you actually need to kind of compute each term individually and then sum them together, which could be slower.
But it's not a premise per se. Like it's not. You are not doing it for the sake of quicker computational time, but rather retrieving the dynamic
right.
an unknown system.
Yeah, our goal at this point is not for prediction. Yeah, we actually just focused on identifying or like discovering equations here.
It seems like everything you talked about were already identified systems, and you're seeing how close you could get to them.
Right.
Have you applied this to any unknown higher dimensional dynamic?
Right, that's kind of our next step. We can probably incorporate with some experiment data. But you still need to have, I think, a fair, good understanding of the candidate functions, I would say this way. Because, if your candidate function is actually poorly chosen, yeah, it's going to be troublesome. It's just kind of the limitation for a single.
Are you developing any techniques to try to figure out what kind of candidate functions are going to be good? I mean,
no, not
based on user behavior.
Yeah, that's a very good question. It will be nice if you can kind of sort of guess the candidate function based on the time series. Yeah, I think if there is a method can do that, I think it will be kind of huge beneficial for the community.
You also should do some variables. It might be good guidance.
Yeah.
There.
Okay, are we really kind of good to see the demo here? Okay, so I have a kind of we have kind of refactored our code, so it's kind of already kind of in a library form. What do we have here? This is kind of utility here. You can see we already started working on the PDE problem a little bit for the ODE examples here, and this is what we have. So we have this kind of utility here, kind of reconstruct coefficients, and for utility for training, and the network itself. The code here is kind of written in TensorFlow. I have some I received some complaint about the TensorFlow difficult to use. Probably I'm gonna switch to PyTorch at some point or maybe JAX. But this is what we have at this time. So we also have this kind of zoo for our our model. Okay, like functional model we're gonna try. It's like pooling, and this is also kind of our model, so we have analytical solutions for these. So, let's kind of try this. 1 to 96 system, okay? So if I could bring an outline here. There are just kind of like several steps. So you start with preparing the training data, and then define your hyperparameters, and then like define the model, okay? And then you just gonna define your loss function, optimizer, and then do the training, okay, and with pruning. And then there's the step here where you can actually do coefficient reconstruction, which will actually return you the the carbon equations here. So here you can see this is the 100 dimension, Lorentz 96 system that we have tried, and this is the dynamical system we cover. Okay, let me go up a little bit, and this is kind of like a little bit of validation here, right? Here is like the data equation, and you define your number of dimensions. And then this is for sampling. Okay, we generate like 6 different trajectories. Each of them will have like time, okay, t, like capital T equal to 10. All right, and then this is the kind of like the visualize our data. Okay, and you define your like a mini batch learning rate. Well, by the way, you kind of use a constant learning rate here. It turns out it kind of works. But I mean, there are a lot of work that you can actually continue, just on the training side. And this is how we actually define a CombOpNet. We already kind of like abstract it to a like class, so you just kind of plug in and play at this time, just as simple as you just kind of create a one-layer perceptron. Right, can I have a napkin here? I can kind of run those. Looks like we have 2 minutes left. Yeah. Okay. Now let me just kind of finish this part. So you define your loss function and your optimizer, and then this is like the trainer. Okay, and then you kind of have your like pruning, set up your threshold, and you kind of start training. Okay, it will just report you the like the error for each epoch, and then you have the pruning, okay, threshold for each epoch. And then there's this part is for like a coefficient reconstructor. Yeah, so we're still kind of like organizing, the document here. Probably make it more readable, and then probably going to like release the code like very soon. Definitely this year, probably in summer or so, maybe earlier. If you guys are interested in, feel free to reach out. Professor Stas is just here. Just you're actually. Like actually work, we can actually continue looking at work. Yeah, I think that's going to be my presentation today, and thanks everyone. Yeah.
Yes, when is the Fortran version of the system going to be done?
Oh my goodness.
Fortran using the 1966 specification.
Well, that one.
I have no clue.
Right, John is God. Continue. Go to 666. Right, John is God. Okay.
Yeah. Well, let's thank Simon again. Thank you.